Hi, this is an explanation for problem 105 in chapter 12. This problem reads, the surface area of an adult human is about 1.8 meters squared. Suppose a person with a skin temperature of 34 degrees Celsius is standing with bare skin in a room where the air is 25 degrees Celsius, but the walls are 17 degrees Celsius. Part A then asks, there is a dead air layer next to your skin that acts as insulation. If the dead air layer is 5 millimeters thick, what is the person's rate of heat loss by conduction? Okay, so to go about solving part A, we're going to use this equation right here where Q divided by delta T, so basically the rate of heat loss is going to be equal to a constant value K times the area divided by the dead space insulation area times the difference in the temperatures by the delta T. Okay, so to derive all these values, K is just going to be a constant value, like I said, so that's just going to be 0.026. The area we were given in the problem, 1.8 meters squared. The delta T is simply going to be the human skin temperature minus the air temperature. So, I mean, you can convert it to Kelvin first if you want, or you can just subtract it by Celsius. Either way, you're going to end up with 9 degrees, and then it's just going to be 9 degrees Kelvin. And then that's all going to be divided by the 5 millimeters, but we need to convert that to meters. And so it's going to be the 5 times 10 to the negative third meters. So when we run all that algebraically for part A, we're going to get 84 watts. Alright, so after solving part A, part B then asks, what is the person's net radiation loss to the walls? The emissivity of skin is 0.97. Now, to solve for this, we're going to use an equation right here. The net change in heat divided by the delta T is going to equal E, which is the emissivity constant that we were given in the question, times this symbol right here, which stands for Stephan's constant. Again, this is another constant value. It's equal to 5.67 times 10 to the negative 8 watts per meter squared times Kelvin to the fourth, so kind of a crazy constant value. And then it'll also be multiplied by the area, and it'll also be multiplied by the change in temperature from the body to the walls. Alright, so if we plug in all of our values, whether we're given them in the problem or whether we derived them, we're going to end up with this equation right here, 0.97 times 5.67 times 10 to the negative 8 times 1.8 meters squared times 307 minus 209. And then we'll end up with 179 watts. Okay, part C then asks, does conduction or radiation contribute more to the total rate of energy loss? Now if we go back and look at how much energy we lost to each, in conduction we lost 84 watts worth of energy, but in radiation we lost 179 watts of energy, and so the answer to C is going to be radiation plays more of a role in the loss of heat. And finally, part D asks, if the person is metabolizing food at a rate of 155 watts, what does the person feel, or does the person feel comfortable, chilly, or too warm? So simply here we just need to compare how many watts are leaving the body versus how many are coming in. And so we already solved for how much heat energy is being lost through conduction and radiation. And so I went ahead and added those two together. 179 plus 84 equals 263 watts. And then the problem told us that they are metabolizing 155 watts. So if we subtract 263 from 155, we actually get a negative value of negative 108 watts, which means they're probably going to feel chilly.